Hello everyone, good morning, good afternoon, and good evening. I hope that you are all doing well and staying safe. On behalf of SPE University of Boomerdale Student Chapter, I would like to welcome all of you to our virtual software internship. My name is Nabil Awidad and I will be your moderator for today's session. So today we have a session about ResFrac software and its applications to optimize shale development. It will be delivered by Mr. Marc MacClure. Mr. Marc MacClure established ResFrac in 2015 to help operators maximize value through the application of advanced geomechanics and reservoir simulation. Before founding ResFrac, Marc was an assistant professor at the University of Texas at Austin in the Department of Petroleum and Geosystem Engineering. After earning a Bachelor of Science in Chemical Engineering and a Master of Science in Petroleum Engineering from Stanford University, Marc earned a PhD in Energy Resources Engineering at Stanford. His academic research is on hydraulic fracturing, proppant transport, diagnostic fracture injection test, induced seismicity simulation and statistics, and also enhanced geothermal systems. So before we start, I would like to remind you to keep your microphones muted and to drop your questions in the chat box. Mr. Marc, the mic is yours.
I was on mute. Thank you so much for the introduction. Very excited to meet with you guys today. I would encourage you to ask questions as I go along. So one easy way can be the chat box, and I can check that out as we go along. So please don't hesitate. And so my objective today is to tell you a little bit about optimizing hydraulic fracture design and well placement in shale. I'll definitely tell you about my company's software and what we do within ResFrac, but don't want to make it too specific to our company. I want to talk more generally about kind of the engineering problems that we solve, which I hope that you guys find interesting. This is a pretty shale focused talk. That's about 90% of the work that we do within our company. Maybe 5% is on geothermal energy, hydraulic stimulation, and another 5% on miscellaneous. But really, we'll focus on shale today. Yeah, so thank you for the introduction. Just skip ahead here maybe to the purpose of what ResFrac does. Our company makes a combined hydraulic fracturing reservoir and wellbore simulator. So actually, I'll skip to this slide. So you guys might be familiar with Eclipse or CMG. Those are reservoir simulators. They describe multi-phase flow in reservoirs. But they don't simulate hydraulic fracturing. So hydraulic fracturing is injection of water, propagation of opening mode cracks through the rock, pushed forward by the water that you inject, and the placement of proppant into those fractures. Historically, there have been specialized modeling tools used to simulate hydraulic fracturing. That includes codes like StimPlan, Gopher, Frac Pro, Kinetics. But the challenge is that frac simulators have not conventionally had the capability of reservoir simulators. And I think that's historically. In conventional formations, we often, in a reservoir simulator, will just treat the hydraulic fracture around as causing skin, right? And you just change the the productivity index of the well, and that accounts for the near wellbore effect of the hydraulic fracture. But when you get into shale, really hydraulic fracturing creates the reservoir, right? So in shale, we usually have permeabilities of hundreds of nanodarcies, and so I'm sure you guys are all aware. In shale, we're drilling wells in the direction of the minimum principal stress, and it creates. Then we do multi-stage hydraulic fracturing along those wells, and create an array of fractures along the well that are perpendicular to the well. That accesses a tremendous, much more amount of reservoir rock, and that really has enabled this explosion of production in the U.S. and now in other countries like Argentina. So our company predominantly works with US, Canadian, and Argentina shale operators to help them decide how to pump these hydraulic frac jobs, how to space the wells, and solve other engineering and reservoir engineering, completions engineering problems on these topics. So actually, I'll skip ahead, skipping all over my slides here. Here's a list of where we've worked pretty much every major shale play in North America. So, Midland Basin, Delaware Basin, Eagle Ford, the Scoop Stack in Oklahoma, the Haynesville, Bakken, and then up in Canada, Montney, Duvernay, Utica, Marcellus. We have worked with clients or have done projects with all of them. And also we do work in the Vaca Muerta. And our company specifically, we developed this software consulting projects on behalf of operators. So if largely the bigger operators that are a little more sophisticated and have more manpower, they want to run simulation studies in-house. But smaller companies or companies that are just getting started and they want to kind of experiment and see what the code's all about, they'll hire us to do the work ourselves. So we have a team of people that do consulting work, and then we have a team of software developers developing the software. So we really do both. And so that's kind of what we do. Actually, let me continue along this thought. So as I said, conventionally, these frac simulators, they don't have reservoir simulation capability. And so that's really awkward in shale because like I said, you're really creating the reservoir, and the multi-phase production period is so completely impacted by the fracture geometry, the proppant distribution. And then we also get into a lot of kind of more advanced topics where there is truly simultaneous multi-phase flow and fracture mechanics processes happening simultaneously. So there's a term called parent-child, and the idea there is a parent well may be a well that was drilled, fractured, and produced for several years previously, and then we drill new wells near that legacy well, that parent well. And the parent well has been depleting pore pressure in the rock, and so that actually decreases the stress in the formation. And that zone of lower stress around the parent well tends to cause hydraulic fractures from neighboring wells to propagate over towards the parent well. And when that happens, we get frac hits. And so fractures from the new wells, which are propagating and full of high pressure water, they hit the fractures of the parent well, which are closed and low pressure and depleted, and start injecting into them. And so you have water displacing hydrocarbon or proppant from hydraulic fractures that have been producing for many years. And those hydraulic fractures are reopening. There's fluid cross-flowing into the well. Proppant is remobilizing. And all of that is happening simultaneous with things like fracture propagation and stress shadowing and crack opening. So those are situations where the physics inherently involve multi-phase flow, as well as hydraulic fracturing, as well as flow in the wellbore. And so there has been this need for years to have a tool that solves all of the equations simultaneously, captures all the physics simultaneously, and allows us to really get the right physics and solve these challenging problems. So that's what ResFrac does. We are the only commercial software that can do that. It's a true hydraulic fracturing simulator. It's a true reservoir simulator. It's a true geomechanics simulator. It does all of this together in one fully coupled model. So that's our unique angle. And we've been growing very rapidly. We've been commercial for 3 years. And I recently saw a survey saying that among shale operators, we were the #2 used frac simulator and the #2 used reservoir simulator. But different companies made that frac simulator and that reservoir simulator. So perhaps if you took the average, we're the #1. So it's growing very rapidly just because of this technical advantage that we have. So here's a movie of that. What we're going to see here, this is 5 wells. So we're going to fracture this well, then fracture this well. Then we're going to produce those 2 wells for 5 years. And that changes the stress and the pore pressure. Here's pore pressure. So now we're going to fracture these 3 wells surrounding those wells. And so we're getting frac hits and movement of fluid from one well to another, and a lot of crazy stuff like that happening. And so that's the kind of thing that we're able to simulate with ResFrac. Okay, so that's what we do. And now finally back to what's our purpose. What's the goal of the company? We're helping operators maximize return on investment. I think it's really easy when we go to school, especially for people like me who have a PhD and have been a professor. It's easy to go off on interesting, questions and forget what's the point of all this, which is to help operators maximize return on investment. And so that's really the lodestar of our company as a commercial enterprise. And so we have identified the key design decisions that operators make as they are deciding how to develop a shale resource, and we help them optimize those design decisions. So what I'll talk about today is what are those key optimization variables? What are some of the considerations that have to be taken into account when deciding how to pump the frac jobs, how to space the wells, and things like that. So those are cluster spacing. It's going to be targeted. There's multiple Wolf, Sprayberry, upper lower. There's the Joe Mill. So there's all these different potential targets, and so wells are not just all laterally offset, but they're vertically offset in different layers. So all those sorts of decisions are quite complicated, and deciding where to put the wells is a huge multi-million-dollar decision with huge multi-million-dollar implications for the company, and really the overall performance of the whole enterprise depends on getting these questions answered as best we can. But of course, it's a challenge. So that's what we do. Helping them design limited entry, proppant and fluid volume, mitigating problems from parent-child interaction. And more recently, we've gotten involved in some kind of more next generation and exciting topics. Enhanced oil recovery in shale through huff and puff injection of rich gas is a very exciting area. Geothermal energy, using hydraulic stimulation to improve production from geothermal energy. So those are some of the other things. And ultimately, this figure here shows what it looks like when we perform a study. At the end of the day, we want to make a plot of production versus time for different designs. So what we're going to do is we're going to set up a model that represents the subsurface. We like to calibrate to at least one existing data set first, and then run prospective scenarios and say, okay, well, if we changed this parameter or changed that parameter, how would that impact this company's return on investment, and help them make the best decisions that they can. Part of that is this process of continuous improvement. So I think what's really important to note about shale is just how much better we've gotten at it in the past 20 years. Frac designs from 20 years ago were extraordinarily inefficient compared to frac designs of today. Recovery factors in shale are probably reaching 20% now. That's the latest number I've heard from a major operator. That's not bad, and it's probably 5x higher than it was 20 years ago. So there really has been extraordinary improvement. And the reason why that happens is that every 3 to 6 months, they drill a new set of wells and they get back production data. And once a well has been on production for, let's say, 6 months, they already have a pretty good idea of how that well is going to be long term. And also, there's pretty steep declines, and so the economic returns are largely dominated by the first few years of production. So companies are getting really nice feedback really quickly to help them kind of see what worked and iterate. And that's, that facilitates improvement. It's still been very inefficient though. It's taken many, many years to get to the designs that we use today. For many, many years, people used inefficient designs. And so the goal of a company like ResFrac is to help, did I do that? That green line, that's funny. The goal of a company like ResFrac is to help operators iterate faster. And even today, even in 2021, companies are continuing to see substantial improvements in their performance. They're encountering new problems and having to solve those new problems. So there's still a lot of work to be done, but it's taken a long time. But really, again, shale really facilitates improvement because of this feedback loop that we get. We could compare that to something like a water flood in a conventional reservoir. You only get to do the water flood once, right? And in 30 years, we'll know what the field's ultimate recovery was, or in 60 years. And you can't go back and try a different water flood pattern and see how that would have impacted the field, right? And so it's harder to get that feedback loop in a lot of our petroleum engineering applications. Sometimes we never get a feedback loop, and so we're flying blind. But shale, we really do, and that's really facilitated improvement. I got a chat question here. Said I'm not very loud. Okay, well, I'll move the computer a little bit closer to my mouth. I hope that helps. Not sure what else to do. Thanks for letting me know. So that's kind of what we're trying to do. Also like to talk about, how do we fit in with everything else? So how do companies improve over time? They do a variety of things. One of them is statistical. They'll just, you've got a well database on Inverus.com. They can download the performance of offset wells. And there is some public data about some of the design variables, and they can just try to identify correlations between production and inputs like proppant volume. And that has some value, but it has limited value because, first off, those sorts of statistical analyses are missing a lot of the key design variables that have a huge impact on production. Secondly, you can do lookbacks on past production, and that will tell you about the past. But if the best design is something that isn't in the past production data set, you can't predict that. Statistics allows you to interpolate between observations, not make novel predictions about something that's different from what you're doing now. We can run lab experiments, but lab experiments are useful, but the field scale is very different. It's different size, it's usually different pressure, temperature, and things behave differently at different scale. And so lab experiments have some value, but they're not perfect. We can hire experts and ask expert opinions, and that has some value, but also experts are human beings, and experts are not always right. Often they're sure they're right, but they're not necessarily right, and sometimes they're really wrong. So just like everything else, experts are just one more data point. They also like to collect field data. So for example, microseismic data is one of the earliest and most widely used types of field data in shale, but microseismic data is imperfect, right? So first of all, it turns out that sometimes microseismic frac lengths are very inaccurate, I've now learned. But also it's just a very kind of coarse and interpretive representation of what's really happening. And still, it's helpful. So we have to take all this data, put it together, and try to make a decision. And so what we do within ResFrac is we do, physics-based modeling, where we try to build a numerical model that represents all the key physics and tries to capture, everything that we think is. I don't know how to get rid of this weird green line, but anyway, we try to capture all the key physics, calibrate the field data, and then help companies make a decision, and it fits in with all these other sources of information to help them iterate faster. Ultimately, what's king is to go out and drill the wells, fracture the wells, produce them, and see what happened. And that's ultimately how we learn and improve. But we would like to do that in a way that's efficient. We don't want to go out and drill and fracture and produce a bunch of wells using bad designs that we knew at the beginning would never going to work. And so what we want to do is iterate towards the best answer sooner. And that's what we're trying to accomplish in Shale. Okay, so I think I will move on to the next topic, but I think I covered that. Yeah, so any questions before I move on?
Actually, so we have one question.
Okay, yeah, so someone's asking by statistics. Oh, go ahead.
Yes, it's that question. Statistical analysis. Do you mean machine learning implementation to find the correlation?
Yeah, I mean, machine learning, statistical analysis, AI, they're all kind of the same thing, which is to look back at training data and identify patterns, right? And that is a good idea. I think that's smart, but it's a big mistake to think that's everything. And so here's an example. I was talking to a woman who was working with a shale operator, who's a very senior person in a shale operator. And she said that their data science team had gone back and they had done an analysis of production data. And the data science team said, when we use shorter stage length, we get better wells. So shorter stage length means, we isolate sections of the well with plugs and we inject into sections of the wells. So they had found that their wells with more stages in shorter length were producing better. Of course, that's costly. It actually increases the cost of the frac job to use more stages that are smaller. But they were spending the extra money because they believed they were getting better wells. And that was a valid conclusion from the data science. And in fact, that may have even helped them make better wells because they actually were better wells. Problem is, there was a new solution, a better solution that they hadn't ever tested. And so the data analytics team was missing it. So the reason that their shorter stage length was helping is because when they used longer stage length, they were getting poor perf efficiency. So if they had, let's say, a 250-foot stage, they weren't breaking down and propagating a fracture from every perf cluster. So if they used shorter stages, that helped them make better perf efficiency. They got more fractures and better wells. Well, there's cheaper ways to improve your perf efficiency. So rather than pump shorter stages, it turns out that the best solution was to use better limited entry completion. So there's perforation pressure drop, which scales with the flow rate out of the wellbore, quadratically with the flow rate out of the wellbore. If you use a limited entry completion design based on perforation pressure drop, you can achieve good perf efficiency with longer stages. And that's the optimal solution. So they're physics-based people, which in this case was basically just their experts who understood how hydraulic fracturing works. They said, no. What we need to do is we can use the longer stages, but we need to improve our perforation design and we'll get better perf cluster efficiency. And so when they made that change, they arrived at similar production results, but then they didn't have to spend the extra money to have the shorter stages. So that's my point, is on the one hand, the data science did give a meaningful result here, but it wasn't actually the best solution. It was just the best solution in the subset of things that they've already done. And if the best solution is something that you haven't already done, then machine learning is not going to tell you that. And so that's why it's useful, but it's not the only thing. And we still have to do engineering on these systems. Also, I talked to a lot of operators that try machine learning, and sometimes they just can't, get good results at all. One problem is, public data sets don't have all the data. They have some information, and so you can draw some conclusions, but it may be that there are key design variables that are changing that you don't know and you don't see in your analysis, and that destroys the results, or it prevents you from getting good results. So these are just some of the challenges. Another challenge is often things are changed at the same time. So like around 2015, people abruptly changed like several aspects of their frac designs. And so if you've changed things in concert, you can't parse out the relative impact of different changes. So these are just some of the limitations of those sorts of approaches.
Okay, thank you, sir. Have seen data point of view. Are we able to do what-if analysis on hydraulic fracturing previous designs in order to know what's better for the entire field we are working in?
Yeah, that's exactly what we do. So our workflow is essentially that we will. I wonder if I have a workflow slide. I may not have a workflow slide in this presentation. Let me see if I can find one. Yeah, here's our workflow slide. It's a great question. So the workflow looks something like this. We have a kickoff meeting. We gather all the data. So we need geologic information. And what we want to do is we want to have a calibration data set, because we do want to make sure that we tune to some field data before we apply to what-if scenarios. So we'll pick out the client, the operator picks out a calibration data set. We set up the geologic model, we import the frac schedule, we've got the production data, and then any other supplementary data that we have that we're going to calibrate to. So we run that model as an initial model, we compare with observations like production, and then we do a calibration step where we modify inputs to the model to be consistent with the calibration data. Once we've done that, then we run what-if scenarios to assess, hey, if we changed this or that, how would that impact production? And so that's what I'm showing like in this early slide here. This is a paper from a paper we wrote with QEP in the Midland Basin. So we have evaluated different frac designs, and basically design 3 here is outperforming the other designs. And so that's the design that was ultimately recommended to the client. So that does allow that kind of what if, scenario stuff. And that could be a design they've never done before. And so they can't apply machine learning to predict that. They have to just try to extrapolate out of their data set using physics. So I think we had more questions.
Okay, we have one more about, it's about the governing equations.
Yeah, so this is a simulator. So first off, if you want a huge amount of detail, if you go to our website or you Google ResFrac technical write-up, we have a very detailed technical write-up of how this thing works. So it is a numerical simulator, which means that it is very general. So well testing equations are analytic solutions based on a lot of simplifying assumptions, things like, usually assuming single phase flow, for example. This is a very, in contrast, ResFrac is an extremely general tool. So what we do is in a simulation tool, you split up space into elements. So here we have matrix elements, fracture elements, and well elements. And then we solve the governing equations in every single element, and then we do time stepping. So in time step 1, we basically advance forward, 1 minute in time. And then we solve mass balance in every single element. And that is mass balance for the hydrocarbon, for the water, for proppant. We might do an energy balance. We might have water solutes like frac fluid, like gel. We have to transport. We have to deal with mechanical equilibrium equations. So as the fractures are opening, they cause stress shadowing and deformation in the formation. We have to calculate that. As the pore pressure is depleted, we change the stress in the rocks. We have to be calculating those in a way that's adaptive and implicit in time. So we have to solve all those equations simultaneously. And then we take thousands of time steps through the full thing to simulate what's happening. So it's the governing equations are, mass balance, energy balance, and then things like Darcy's law, and equations like that. So it's got a tremendous amount of detail in it. I think it is fair to say, it's probably fair to say, well, the combination of diverse physics into one numerical tool is I think truly unique. It is probably the broadest set of physics available anywhere, in this industry. Doesn't do everything, but for Shale, it does a tremendous amount. So I'll pull up the technical write-up here somewhere. There we go. So again, you can just find this on Google, the ResFrac technical write-up. Go through the gridding, system of equations, fluid flow and fractures, matrix and wellbore, thermal transport, ton of information on proppant transport, water solutes, stress shadowing, on and on. Hope that answered the question. And then I think there was a question about plotting. Sure, let me show you our user interface. So this is a simulation of a huff and puff enhanced oil recovery in shale. And so we have this 2D line plotting capability. Then we can skip around in time. So maybe I'll go 6.5 years. So here we can see this is during a production period. We can see depletion up there. I can change different parameters I might want to look at. So I'll look at gas saturation. Okay, so it looks like in this simulation, it's injecting into this well right now. It's injecting gas into this well. We see a lot of gas here. Pressure's high here, low here. Fractures are intersecting. A lot of optionality here. So I can plot all sorts of different things up here in this line plot. I can add different things like wellhead pressure or rates. I can have multiple panels. So this is all a custom-built visualization tool specific to our simulator. And here's our user interface in general. Here's like a set of simulations. Here I can pull up the builder. So the simulation builder is going to help me set up simulations. And there's a lot here. You've got things like built-in tutorial movies. If I click here, you can go to this. There's a movie What else? Yeah, so I can make this full screen. We got pictures and all sorts of built-in help content within the user interface. I can preview things. So like if I went to let's say go to fluid properties. So it supports compositional or black oil. Here's a compositional model. If I don't know what compositional model to use, I can actually, there's a wizard here to help set one up for me. And then I can preview that compositional model. So if I click this button here, it's going to do a constant composition expansion. So here is basically volume versus pressure as the mixture is expanded. So tremendous amount of work and investment has gone into all this user interface stuff. And a lot of this is online. So if you check out our website, you want to see more information about the let's see, the user interface and all that kind of stuff. We have a full simulation training that's been recorded and posted online. So this is a lot more technical background on the specific physical details of what the simulator is doing, physics of hydraulic fracture propagation, key physical processes, and then getting into specifically how to build a simulation within our user interface. All right. Have I addressed the questions? I think so.
Yes, sir. We're done with the questions, and you can continue.
All right. So let's see. Here. Yeah, one of the kind of cool things that's happened in recent years is how field scale data collection has become really good. One of my favorite sources of data is fiber optic. And people put fiber optic cable in injection wells, and they also, recently what they'll do is they'll drill a pad. So let's say they've drilled 5 wells. They can put the fiber in one of the 5. They actually just put it inside the casing, like within the well, before it's been perforated and completed. And then they fracture all the surrounding wells. And they've got the fiber in an offset observation well. When the hydraulic fractures from the offset wells hit the fiber well, they can observe those frac hits. So that's what's shown in this image right here. This is actually the strain response as a crack approaches and then has passed a well. It's pretty remarkable. This strain response, by the way, looks very similar to the analytic prediction from classical fracture mechanics, which is kind of incredible. And a great validation of theory, by the way. With this kind of data, we can see when each individual hydraulic fracture is reaching an offset well. So we get an idea of how many fracture strains there are, how long they are, how fast they propagate, how symmetrical they are, things like that. We have a lot of other really quality information like that. And so when we put together all of the information that we're getting, geochemical fingerprinting, pressure observation wells, companies are even doing things like that, interference testing, we start to get a really good idea of how long the fractures are, how high they are, where the proppant went, where the production's going. And so, we do have the pieces in place to do physics-based simulation. It isn't a situation where it's so complicated we don't understand it. We actually understand a lot. And I think our understanding has transformed a lot in the last 10 to 15 years as operators have improved the field scale data collection that is possible. And so that's really what enables us to do this kind of modeling. So here's an example this is a paper that was written by QEP using ResFrac on optimizing their development in the Midland Basin. And so a couple kind of things to note here. In the bottom left, we're looking at pressure and stress change. So note how these hydraulic fractures are very kind of unpredictably shaped. So some go up, some go down, some go left, some go right. And that's not something that we assume. It arises from the physics. So as cracks propagate, they create an increase in stress around their sides. That's called stress shadowing. And that tends to make them kind of try to get out of each other's way. And so they have these kind of heterogeneous shapes. And this is very consistent with field data. I think it's quite realistic. In the bottom right here, we're plotting different things against time. So for example, within a stage, there's different perforation clusters, and they can take different flow rates. And so what we're plotting here is flow rate versus time into the different perforation clusters. The perforations can erode, so we're showing erosion here. So really just showing how we can output a lot of really interesting information. And again, ultimately, what we do is we can evaluate different frac designs and assess which one we think is the best. Here's kind of an interesting topic that I've talked a lot about recently, not recently, for a long time. What is the fracture geometry in the subsurface? So I was in graduate school a decade ago, and at that time, it seemed that everyone believed that hydraulic fractures in shale created a very branching kind of, zigzaggy network of fractures. And so around that time, Schlumberger was releasing kinetics. Here's an image from one of their papers. And what we see is that fracture pathways, they go out, then they turn like 90 degrees, and they turn another 90 degrees. This very zigzaggy, networky like fracture network. And it seemed to me that that was what everybody thought was happening. But now, 10 years later, really the industry in shale is kind of congealing on a very different understanding of what the fractures look like. And it comes from direct observation. So companies, again, putting fiber optic in offset wells, they're finding that fractures are going very linearly and in narrow corridors. So this is a paper from Shale. They have a fracture well here and a well with fiber. When they fracture this stage, we can draw a straight line in the direction of SH max. You see where the frac hit's going to occur. And that happens all the way down the well. I have a paper that I'm a co-author on with Apache next month at the Hydraulic Fracture Technology Conference, exactly the same observation. They fracture one well, they draw a straight line. That's where the frac hit occurs 800 feet away in the offset well, all the way down the well. Now, occasionally you hit a fault, and that causes a zigzag off one way or the other. But in the absence of major faults, which is the majority of the time, majority of stages by far, just get a bunch of straight lines. If you look at the fiber optic response, the strain field ahead of these fractures looks exactly like the propagation of an opening mode fracture. And there's even recent projects where people have cored through the SRV created by hydraulic fracturing. And when they've cored through, what they've discovered is a bunch of parallel hydraulic fractures. And so it appears, based on direct physical measurement, that the kind of image that's conceptualized by these kind of branching complex fracture networks is just not representative of what fracturing actually looks like. Not to say that no fracturing in the world has ever looked like what's shown down here in the bottom left, but it certainly appears that the vast majority of the time it doesn't. And I used to say that 3-4 years ago, and it was kind of an unpopular thing to say, or it was a little tricky to try to say. And in 2021, there's only a couple major companies in the industry left that are not on board with this realization. So there are still a handful of companies that are really committed to the idea that hydraulic fracturing creates a branching kind of zigzaggy fracture network, but 90% are on board with the linear fracture propagation, and it's just based on actual data. So anyway, I think that's an important FAQ. People ask, well, Mark, why are your images not showing these zigzaggy pathways? And it's because I don't think that exists in real life. And so it's been a big change that's been driven by these operators that have gathered this really spectacular data. So what does the flow pathway actually look like? It appears what happens is we create these basically linear hydraulic fractures, and then fluid just flows into them from the sides. But since the fractures are rather kind of irregularly shaped like we see here, the distribution of pressure is actually quite patchy, right? So there's areas with a lot of depletion, and then there's areas with very little depletion. And this happens because the permeability is so low in the formation that you can get this patchiness. Now, eventually, the adjacent fractures in a well will interfere, and we can see that in rate transient analysis plots. But that's okay. You actually want to design the system so that the fractures interfere, because if they didn't interfere, then you're not draining efficiently. All right. So what I'm going to do next is just talk through some basic optimization type concepts. What are some of the main design variables that we need to optimize? The first and kind of most basic, but very important, is cluster spacing. So the idea here, first off, these days, almost everyone does plug and perf completion in shale. So to take a step back, what a plug and perf completion means is you cement the casing or liner into the well, all along the lateral. And then you perforate out in a series of stages. The alternative would be to use swellable packers, where the liner is not cemented into the hole, but rather is just hung open hole in the lateral, and then these swellable packers isolate sections. Nobody does the swellable packer thing anymore. Nobody is a strong word, but I rarely see it anymore. It turns out that if you have a 300-foot section of open wellbore, even in a horizontal well, that when you do injection into that section, if it's an open wellbore, that fluid will tend to create about one major crack, because fluid takes the path of least resistance. Maybe it makes a couple hydraulic fractures, but that leads to very inefficient drainage, because the permeabilities of the formations are on the order of 100 nanodarcy. And so if you have 300-foot stages and you put a fracture every 300 feet because you're using an open hole swellable packer completion, you're going to have huge swaths of the reservoir that are completely undrained, and you will have low recovery factor. And that is essentially what happened for many years in shale. But since then, what people have discovered is we want to put the fractures a lot closer together. We want them to interfere, and we want to force fractures to form. And so the way that you force a fracture to form is you use perforation pressure drop. So we cement in the casing. We blow perfs every 20 feet, and the perforation pressure drop forces fluid to flow into every single perf cluster, or nearly every single perf cluster. And now you're creating a fracture every 20 feet instead of every 300 feet. And so if we look here in the bottom left, here's an image from the Utica Shale simulation, and the axis is stretched. So these fractures are actually much closer together than they appear. But here's with a wider cluster spacing. Here it is with a tighter cluster spacing. Well, you want blue. You want a lot of pressure depletion to take place. And if you put the fractures too far apart, you just get these big empty regions of no depletion. That's exactly what's been observed in field data. So years ago, people were putting the clusters much further apart. Nowadays, they're putting them 20 feet apart. Say maybe it's 15, maybe it's 30, maybe it's 35. It depends. It depends on things like the permeability and so forth. But it should not be 50 pretty much ever, and it certainly should not be hundreds of feet. And so this is one of the key design optimizations that we look at. Got a question here?
Yes, we have a question about the depth of investigation.
Yeah, go ahead and just ask the question if you want to turn on your mic. Are attendees allowed to, or are they able to unmute? Oh, here we go. Yeah, so what are the parameters to consider? And what's the depth of investigation? Well, ultimately what we do is we run a modeling study to decide the cluster spacing, because there are quite a few considerations. So yeah, if as you put the clusters closer together, let's say you're going to pump a 200-foot stage, and you've decided on the amount of proppant and water that you're going to pump into that stage. So let's hold that constant. That means if you add perf clusters to the stage, you're reducing the amount of water and proppant per cluster, right? So in that case, you're actually probably going to get shorter propped lengths and shorter fractures per cluster. So that's one trade-off. As you add more clusters, if you keep fluid and proppant constant, then adding clusters shortens the fractures. And so that's a disadvantage. If you increase proppant and fluid volume as you increase the number of clusters, you're increasing cost. So there's a cost there too. So there is an optimization to be performed. So that's one consideration. Second consideration is, yeah, of course, there is a region of interference between the fractures. So we can see in this image here, obviously, these adjacent fractures are severely interfering. Now that's okay. You actually want them to interfere. If they don't interfere, then your recovery factor is not very good, right? I mean, you don't want a huge pressure gradient to develop between the perfs after 5 years. You want to have it pretty uniformly low everywhere. That's the goal. So that requires interference. So you want interference, but you still don't want them to interfere too much. So there is some cost there. But on the flip side, as you add clusters, you're creating more pathways for flow, right? If you're producing into 10 hydraulic fractures, that's more production than if you're producing into 4. These fractures are effectively close to infinite conductivity. So fracture conductivity is less important because the permeability is so low in the rock that you don't need much fracture conductivity to get good production from the formation. So you don't need to place big, thick, high conductivity fracture pathways. You just need a lot of fracture pathways. And so that's why you need to make more. So what we're showing here on the right, this is an optimization of net present value versus cluster spacing from a Utica Shale generic example. What we're saying is for the low permeability model, which was actually the right permeability model, the optimal cluster spacing in our example was about 25 feet. If the permeability had been much higher, the optimal spacing would have been 75 feet, but it wasn't. It's very low. So permeability is probably the biggest geologic uncertainty that impacts the optimization. And really, permeability estimation in the industry is a huge mess in shale. The service companies give really inaccurate permeabilities sometimes, not always, but sometimes it's really bad. Actually have an SPE paper that's coming out in December about this. What we did is organize an entire industry study with 7 operators looking at using fracture injection testing to estimate permeability. And we developed an entire procedure start to finish. So I'll pull up that paper quickly and show it. We focused on this because when I talked to operators, they said, this is our biggest uncertainty. This is the most important thing. It's hard to measure permeability in shale. And even if you use lab experiments, the field scale permeability isn't necessarily the same as the perm you measure in the lab. So this paper here, we developed a step-by-step comprehensive DFID interpretation procedure with Shell, ConocoPhillips, Apache, Range Resources, Hess, and Equinor. And in key ways, this procedure deviates pretty substantially from the way that you would get from a major service company. And to show where that matters, we've since run a lot of DFIDs for operators. So we've written a paper, which is not yet out. It'll be at the International Hydraulic Fracturing Technology Conference later this year. Pulling it up here, where we statistically compared 62 DFIDs from 9 different shale plays contributed by 10 different operators. And they're all anonymized, so you don't see where they're coming from. But just as an example of how inaccurate it can be, so this is comparing what we believe is the correct permeability estimate in these tests to a method called the holistic method, which is if you buy the new SPE hydraulic fracturing textbook, it has this equation, this holistic permeability equation in it. And what we're finding is on average, it is 226 times inaccurate. And the inaccuracy can be anywhere from 3x to over 1,000x wrong. So our conclusion is that this method, which is in the new SPE textbook, is like severely, radically inaccurate. And it's used out there in industry. And when you take those permeabilities and you put them into these sorts of optimizations, what you'll find is it gives you things like the cluster spacing should be 75 feet when it should really be 25 feet. And the impact on net present value would be the difference between being here and here. You lose a lot of money on those estimates. So permeability is one of the most important, and that's why we've focused a lot of effort on it. It's not only one of the most important, it's one of the most commonly inaccurate numbers in shale. And so we've put a lot of effort into that. What else? You got to be able to maintain good limited entry completion. So you do need to have good perf efficiency. if you put the clusters too close together, they can start to communicate outside the casing. So when you pump a frac job, you do tend to create a longitudinal fracture outside the casing, at least some distance from the perf clusters. I've heard that estimated to be as long as 20 feet. And so probably when you do 20-foot cluster spacing, they probably are communicating to at least some extent. But as they get closer to closer, it gets more severe. So if you go out and you pump a 10-foot cluster spacing job, you're very likely going to have a lot of communication between the clusters. And that actually defeats the limited entry, and it prevents you from getting the distribution of closely spaced fractures like you want it. So that's an issue as well. I'm sure there's others I'm not thinking of. I mean, it's affected by things like well spacing. Really, it's all an integrated optimization. So these are some of the considerations, but ultimately, you need to optimize cluster spacing with well spacing, with proppant and fluid volume, with your perforation design. And you've got to do that with a calibrated model that encompasses solid field data as well as the right physics. So that's pretty much how we do it. That's our approach. I hope that answered the question. Long answer.
Okay. Yeah, thank you, sir. We have another question. It's about how to ensure the best distribution of the frac fluid in each cluster in the plug and perf technique.
Yeah, well, I mean, the first line of defense on perf efficiency is without question limited entry completion. You should have a small number of shots per cluster, and you should have relatively limited shot diameter. I think these days people are moving to like 1 or 2 shots per cluster. And the reason why is because, again, the flow rate down a perf cluster is proportional to the square of the flow rate. So if you try to put 100% of flow into one little perf cluster, it'd be a ridiculous amount of delta P, and it would break down the other clusters. And so limited entry completion is by far your most important tool in the toolbox. It's not everything, but it is definitely like number one. You can think about the shot phasing. Recent work by ConocoPhillips with downhole imaging and fiber has shown that, like, if you do top bottom 180 perf phasing, that you get a lot more erosion in the bottom cluster. So ConocoPhillips has been recommending, and I think what they're saying is absolutely right. ConocoPhillips has been recommending 0% phasing, so putting the clusters only on basically every cluster is one shot, and it's along the top of the well, and that is probably the current best practice. Now, it does increase cost to do limited entry because it's going to increase your injection pressure, but it's worth it. I mean, the incremental production is substantial. Other things to look into. It appears that based on the quality of your casing, you're going to get really different amounts of erosion. So the sand particles abrade the shots, and if you get really bad erosion, then that can really defeat your limited entry and lead to like runaway fracs. So companies are now doing downhole imaging where you can go in after the fact and you can see how much the perfs eroded over time. And that's a good QC because you might go down there and discover like these severely eroded perfs that are just dominating flow. So that's important to check on. And another one is the quality of the plug. So it looks like some companies are finding that a significant number of their plugs are not holding. So they end up just pumping back into the previous stage. Obviously, that kills you on your efficiency. So again, I love ConocoPhillips. Another ConocoPhillips paper recently was showing how before you pump the next stage, you can just do a basic like pump in a little bit and then see if the pressure holds. So you just basically like a formation integrity test for your stage. Just pressure up the stage and then just wait for 15 minutes and see if pressure holds. If it doesn't hold, you're leaking back into the previous stage. So that kind of simple diagnostic can be fantastic for assessing the performance of the plugs and can have just a huge impact on your performance of the well. There's also a risk of flow behind the casing to go around the plug. That's not as severe as the plug leaking itself, but that's worth looking at. You might even tighten up, you might widen your cluster spacing a little bit around the plug consideration. You can try diverter. Some companies really believe in diverter and a lot of companies don't. From what I've seen, it might have some incremental benefit. It's definitely not enough. It's not going to, move the needle. It's not the most important thing, but maybe diverter helps. Those are some of my thoughts on that.
Okay,
Yeah,
thank you.
so a question about how do you deal with naturally fractured reservoirs? Great question. It's an FAQ. As I said, first off, even if it is a naturally fractured reservoir, I don't think that hydraulic fracturing looks like a zigzagging pathway. That's point one. What probably happened, well, point two is it's entirely possible that the natural the appropriate way of handling a natural fracture in a numerical model depends on what the natural fractures are like. If you have a very large number of fairly small natural fractures, then you can treat it like a single permeability model. In other words, the matrix permeability is elevated by the presence of natural fractures in the formation, and that's all you got to do. Just increase the permeability. You can consider using a dual porosity treatment to handle that. We have that capability in ResFrac. What I can tell you is that I have not yet encountered a single data set where that was necessary to match any of the data. And I think what that's telling me is that the effect of natural fractures on flow in the matrix is primarily to have an increase in the system permeability. And that appears to be just about it. Thirdly, I question the degree to which natural fractures impact production in a lot of shale plays. In other words, yes, natural fracture permeability is important in some shale plays, but it may not be that important in a lot of them, or maybe most of them. That is sort of what it looks like to me. When we look at natural fractures in core, a lot of times it's just a really hairline feature full of calcite. And is that actually mattering much? Unclear. The permeabilities we use to match production data are pretty darn low, and it doesn't, we're just not getting evidence of really big, heavily naturally fractured formations. And I'm just talking about the US shale plays that I've looked at. So obviously there's naturally fractured reservoirs in the world, of course. So if you are in a naturally fractured reservoir that truly has genuine natural fracture treatment, usually dual porosity is the way to go. And regardless, there's not much evidence to support fracture modeling treatment that looks like that. Natural fractures could also have other effects, like they could increase the effective toughness to crack propagation. So it might tend to make the fractures shorter. But again, I'm going to be completely honest with you. That's a hypothesis where I have never seen even a single field data set that actually truly demonstrated that. So it really remains very unclear the degree to which natural fractures have much of an impact or not from a modeling perspective. That's my view. And I'm saying that as somebody who started my career doing DFN fracture network modeling. And I have just changed my views on that a lot as I've worked with field data.
Okay, thank you, sir. We have another question. It's what is the precision of the estimated depth of investigation? When we fracture the shale, what is the risk of communicating with upper water reservoirs?
Yeah, so I mean, those are almost two topics. So depth of investigation would mean like if there was flow through the matrix into the fracture. The depth of investigation through the matrix into the fracture is quite small, and the vertical permeability is really small. So you're getting out tens of feet from fractures. That's your depth, maybe 100 feet laterally, and vertically it's even less. That's the depth of pressure in investigation in the matrix. I mean, that's a different question from what's the risk of fracturing into overlying or underlying water-filled zones. Obviously, that's totally formation specific. There are absolutely situations where there are very wet layers that contribute to water cut. For example, in the Midland Basin, the Dean is a rather high permeability and very water saturated, or debatably water saturated layer in the Midland Basin. And they do fracture right into the Dean, and it elevates their water cut. So at least in modern shale plays that are economic, Most of them, some of them do fracture into water bearing zones, and they just take the water and they just tolerate it. If largely the fracture height is driven by the stress layering of the rock, and you can't control that, right? That's just a formation property. Fractures tend to grow into low stress areas and away from high stress areas. And so if you are fracturing and you had a low stress zone right above it, it's going to be difficult to keep the fractures out of the low stress zone. And that's just a tough, unfortunate geological situation. There are ideas. I mean, people have talked about using far field diverter to try to mitigate crack propagation into low stressed zones. And there is some evidence to suggest that that can be beneficial. You might consider using a lower viscosity fluid. Typically, thicker fluids will tend to have more height growth. So there are some options there. But yeah, I mean, that's one of the design. If you were in the unfortunate situation where you really did have a like big water filled high perm zone that you kept fracking into, it'd be the kind of thing you'd have to engineer around with something like well placement, far field diverter, or fluid selection. But yeah, I'd say in most of the U.S. shale plays, it's happening. Like it's happening in the Midland Basin for sure, and happens to some extent like the lodgepole above the Middle Bakken, and they just tolerate it. They just produce the water along with the oil. So it just depends on the situation. All right.
Okay, that's all. Sir, you can continue.
Great. So well spacing. This one's pretty straightforward. Fractures from adjacent wells compete to produce the same rock, right? So what I'm showing here on the bottom right is as I tightened up the well spacing, we're getting more overlapping fractures from adjacent wells. So they're competing, and that is going to have a negative impact on production per well. But of course, if the well spacing is too far apart, we have the risk of leaving these large undrained regions. So there's really this sort of balance we have to strike between too close and too far apart. So again, that's the kind of thing we run an optimization study on. It could depend on vertical placement. What we like to do is interference tests. If you shut in a well and you look at the impact on production of the offset well, you can assess the degree to which they are communicating. That can do a lot to inform your future well spacing decisions. Yet again, this ties back to permeability. If you use that holistic permeability equation I was talking about, and your permeability is 200x too high, you can actually create a rate transient analysis matched to the data, but you'll underestimate length. So if you overestimate permeability, you underestimate fracture length. And then since you're underestimating fracture length, you might space the wells too close together. And spacing wells too close together is a thing that companies have done to great costs. So here's just two examples, Wall Street Journal article and a JPT article about companies that tested extraordinarily tight well spacings and ended up getting really bad results and lost a lot of money on these decisions. And these come out of decisions that are made around basically based on things like their permeability estimate. I saw another question come in. Oh, just got it. Thanks. Okay, appreciate it. Let's see. Here I'm talking about the perforation pressure drop, which again, I think is just a really key thing to be aware of. It's kind of like first line of defense. Here's a simulation where we use like 16 shots per cluster. So here, there's not strong limited entry pressure drop to distribute flow into all the clusters. So we just get a small number of big cracks. And it's terrible for production. We can see these really large regions of undrained rock. This is pretty much what a frac job from 10 years ago looked like. And so we've moved away from that. Now we can place the fractures a lot closer together. It looks more like this. But when they get it in tighter and tighter, and really more than anything, the limit is just the fact that eventually there's fluid outside the casing. There's fluid flow outside the casing, and that just prevents their ability to put the fractures closer together. If we could turn off fluid flow outside the casing, we might be at 10, 12 foot cluster spacing in a lot of these plays, but we can't. So we're probably more like 15 to 20, 25 sometimes. Okay, going to stage length. So if we use longer stages, so every section of the well we pump into is a stage. If we make those longer, then there are fewer stages overall. That shortens the job and saves money. But there is a risk. So as you go to more and more clusters per stage, it gets harder and harder to maintain good efficiency. One, because that limited entry is getting weaker and weaker, because if your flow rate per cluster keeps going down, then that reduces the limited entry effect and hurts your perf efficiency. Also, if you pump at 90 barrels a minute and you've got 18 perf clusters, by the time you get to the last perf cluster, you're at 5 barrels a minute, and the proppant can start settling out in the wellbore. And that blocks the well. You're gonna have to go in with coiled tubing, clean that out. That's gonna cost you money, and also it's hurting your efficiency. So probably 15 or so clusters is getting up to the upper limit of how much they can get away with. And you see a pretty surprising range out there of what people really do. So that's a part of the optimization. We want to push that stage length up as much as possible to save costs, but not go too far. In terms of fluid and proppant volume, obviously pumping more fluid and more proppant results in bigger, longer fractures, more area, and better production. But there's a diminishing return, right? So if you just double your proppant loading, you're not going to probably not double production. So you really have to do an optimization. And what's interesting is how variable this is. We see highly respected operators in different plays going anywhere from 700 to 3,500 pounds of proppant per foot of lateral. So that's comparing between different plays. But even within plays, it's really remarkable how different operators think about proppant loading, which is kind of interesting. Also, in terms of proppant type, since 2015, there has been a dramatic shift towards the cheapest proppant possible. So we see little ceramic being pumped recently. There's some people arguing, like Marc Pearson with Liberty wrote a paper arguing perhaps we could pump a little bit of ceramic at the beginning or the end to help get a little bit better connectivity near the well, which I think is an interesting idea. But largely speaking, people are just pumping the cheapest sand they can get their hands on to save money, and they're getting good results regardless. People have even moved recently. I saw a JPT article about wet sand. So traditionally, the sand is mined, and then they have to dry off the sand before they ship it to the well site. They're finding that they can even skip the drying step. So they just get the wet sand directly out of the ground. They just truck it straight to the site, and they pump it down into the ground. They go to locally sourced proppant. So rather than kind of having a few specialized quarries where they take proppant from, they just get it from anywhere and then just pump it. And that is potentially problematic because perhaps they're pumping something that's not really the mesh distribution that it's supposed to be, or that they say it is, but they're just trying to save money. So that's been an interesting trend. In terms of parent-child problems, so this is when you drill a new well near an old well. So they're looking at things like spacing the wells differently, chemical treatments, looking at things like injecting into the parent well to protect it, so that when it gets the frac hit, it's not as severe. A lot of different optimization decisions around this. And actually, our company right now is doing a collaborative industry study. So there are 7 or 8 companies funding the study. So that's companies like Hess, Marathon, Pioneer, SM Energy, et cetera. And we're doing a big collaborative modeling effort with their different data sets to help them decide on better parent-child mitigation strategies. So, one thing I want to finish on is, what's the biggest risk that we face in the industry? And I think that our number one biggest risk is overconfidence. If we insist that we already know all the answers, then we can't improve. And we don't listen to people with different perspectives, and we get stuck. And it's a systematic characteristic of all humans that we all, myself included, are overconfident in our own beliefs. Just across the board, everyone suffers from this. And I think that to be a great petroleum engineer and to really maximize the value that you can create as an engineer, you have to be ready to constantly reevaluate what you believe, listen to alternative perspectives, and be ready to change your mind. And that's what allows us to improve. I think that the other thing that allows us to improve is frankly just competitive pressure. So frac designs in 2020 are way better than 2014, and they're way better than 2008. But in 2014, if you talk to a completions engineer in Shale, they felt pretty great about their frac designs. And what we've learned since then is that a lot of the things that we were certain were true in 2014 aren't true. And so everyone's always convinced, well, now I really do know all the answers. And more than anything else, we just have to keep an open mind and keep striving to improve and be ready to change our mind. And if we do that, then we can continue that continuous improvement that we're seeing in the industry. So that's my parting thought, is just really want to emphasize that there's probably nothing more important than keeping an open mind and using data to test your beliefs and continuing to try to improve. All right, so I will pause there and see if there's any other questions.
Actually, we don't have any question. Okay, there is one.
We got one.
Yes. Plasma frac is still used in the industry nowadays.
I guess I'm not sure. Could you clarify what you mean by plasma frac? I'm not familiar with the term. Oh, so do you mean fracturing like with diesel, or do you mean like fracturing with CO2 or something like that? Well, I mean, my understanding is that I don't encounter anybody who's fracturing with hydrocarbon-based fluid. I know that that's something that has been done in the past and maybe even works great. Hydrocarbon-based frac fluids are probably too dangerous. That's my understanding. Is it's just incredibly dangerous. Fracturing with gas is an interesting idea, and it's something that we can model within ResFrac. So I wish more people did it. Well, I don't see a lot of it. Not to say it doesn't work or that it shouldn't be done, but I don't see much of it for some reason. What we do see a lot of interest right now is enhanced oil recovery. So the idea of just doing a frac job, producing a well, and then coming in a year later and starting a huff and puff cycle with produced rich gas. That has the potential to dramatically improve recovery factors. There's a lot of interest in that. So, again, I don't know, maybe those are being done elsewhere in the industry. I'm not personally seeing it in my experience in Shale.
Okay, thank you, sir. I think you can continue.
Oh, I'm done. Yeah, that's all I got.
Okay, so we are at the end of our session. We are so honored with your participation with us today, sir. And I'm sure that our audience enjoyed assisting to this instructive and informative session. Wish you the best of luck and have a good day. Thank you.
Great. Thanks, guys, for joining. If you have any follow-up questions, feel free to reach out. Send me an email just to marc@resfrac.com.
Okay, thank you, sir.
Thanks, everybody.
Thank you.